So, little sparse today. I'm sure it's somewhat a function of the weather, although, this is life. Sometimes it'll snow like this. So, couple things off the top I kind of already mentioned, but I don't know if all of you were in here yet. On Canvas, you'll kind of see I changed the due date on that Connect assignment, so it is now the same as the Excel, which are both due now at the end of the day next Wednesday, so a week from today. We'll cover, there's about 5 questions. I shouldn't say 5 because you could work on parts of them, but there's probably about 5 or 6 questions where we haven't covered enough material to answer it completely. After Friday's class, you'll be able to answer everything. After today's class, you'll be able to answer all but like 2 of them, and you can answer parts of those 2. There's just be like 1 question each one, talking about like covariance or correlation coefficient. That's what we'll be covering on Friday. Okay, so move that due date a little bit. I kind of already mentioned a little bit as well. Got 4 or 5 of you that I'm having issues still with the iClicker. If you can, go underneath your profile on iClicker, remove your remote if it's was still syncing up to zeros. Remove it and re-register it. That's fixed like almost every person's issue that's I've had. So hopefully we'll get that kind of ironed out and kind of moving forward. That won't present any issues for us. Questions from me before we kind of jump into things today. So where we left off was talking about variance. Just kind of a reminder. We said what we're going to do for every single observation is find that deviation of that observation from the mean and then square it, add them all up. That gives us our numerator. For our population variance, we divide by our total number of observations. For the sample, we said the only difference is we would then divide by the sample size minus 1. Kind of written out in words, right? These are our stats, right? I said also another way to think about the variance is it's like the average deviation from that mean. Excuse me. So if I need to find the average deviation from the mean, the first thing I need to know is, well, what's the mean? Once I have that mean, subtract it from every single observation value for X. Once I have those deviations from the mean, square them, add them all up, and then the final step, divide by our population size or our number of observations for our population data, sample size, number of observations minus 1. I think I said sample observation. If it's population data, divide by our total number of observations. If it's sample data, divide by our total number of observations minus 1. Okay. So we'll get some more steps, more practice calculating this today. I'll go through a couple more examples by hand. Have you guys work on some. I'll show you how we do some things in Excel. But the other thing that we didn't get to was talking about the standard deviation. Okay. So all the standard deviation is, it's the same formulas we have for the population and sample variance. Remember, sigma squared and S squared were our variance for population sample. S and sigma are going to be the population standard deviation and sample standard deviation. All we're doing is taking the square root of the variance. So we're just scaling it. Right? So if the variance was 100, our standard deviation would be the square root of 100 or 10. Right? All we're doing is scaling that variance. Now, Mike, why are we just creating more statistics for the sake of creating more statistics? It's because once we get down the road, standard deviations, by taking that square root, have a pretty nice interpretation for us. Now, we won't see that for a little while, because I think we're not doing this until after the first exam would be confidence intervals and hypothesis testing. But once we get there, we'll kind of see the standard deviation is a little bit more useful when we have to make interpretations. Okay. Any questions there? So we're just scaling the variance there. Whoops. So I've got this old data set where it had like a bunch of every football coach that were on salary. I think this was like in 2010 or something, but they put it out in the newspaper. So I grabbed the data. And so it's kind of interesting because even though this is for like a college football team, it's probably pretty similar to a lot of companies, right? You've got like the head guy, CEO, maybe your kind of middle management. I don't know, the data tech guy is like your janitor, right? So it's kind of representative of like a company's salary distribution. So if I wanted to find the variance in salaries here, very first thing I would need to do is what? The variance is the average deviation from the mean squared. I got to have the mean, right? How do I do that? Simply add all these salaries up and divide by the total number of observations I have here, which I think is 10. Oh, yeah, there we go. All right. So all I did was go through, take every single coach's salary, add them all up, divide by the number of coaches I had in my data set. Okay. So we got this mean of about 134,000. How would I find the population variance? So the next step that I would do is go back up here and write a column right next to the data where I take the first observation, 489, minus that mean of 134.5, I think it was, square that value, write it down. Then go to the next observation, take its value for x, 150 minus that mean of 134, square that value, write that number down. Do that for every single one of my observations, then add them all up, and then finally divide by the total number of observations that I have. Okay. So I would break it down step by step. You can write it all out on one line, right? It gets a little bit long and messy, but right, that's really all we're doing is taking the first salaries deviation from the mean, squaring it. Add to that the second observation's deviation from the mean squared. Add to that the third, the fourth, etc. Right? Now, another thing I did here, and I'll kind of use this a little bit today, which is why I put it on this slide to remind myself to do this, that I said the final step is once you add up all those deviations squared, divide by the total number of observations you have, right? But here, instead of dividing by 10, I just wrote that out as multiplying by 1 over 10. Right? So anytime we divide by a number, it's the same thing as multiplying by 1 over that number. And this will just help us out think about things, I think, in a better way. But this is just like I guess a mathematical, I don't know what's called a trick, but right, it's the same thing, just written slightly differently. Okay. Any questions on that idea? Okay. So hopefully not too bad calculating these variances. Here I got a slide where I actually did break this down step by step as opposed to all in one line. And you kind of see when I've got observations that are kind of close to the mean, like 150, 124,000 were pretty close to the mean. Those don't add a large value to my variance. When I've got observations that are really far from the mean, that's going to add a ton to my variance, right? You kind of notice when I add these all up, I get 147,000. Of that 147,000, 125,000 of it's coming from one observation, right? So I kind of said, when we square these deviations, it over penalizes extremely large deviations, right? So when I've got a value, like the head coach, they're making way more than the average, it's going to add a bunch to my variance, right? Now, some observations don't add as much. And then once I add them all up, my final step was dividing by the number of observations I have. So I'm really getting kind of like an average deviation from the mean across all of my observations, right? Some of them are going to add way more than 14,000. Some of them are going to add way less, right? The variance is just kind of an average of the deviation from that mean squared. Any questions on that? Yeah.
Is there like a template for this on Excel? Like one you could provide there, or just
do
it all by hand?
So we did last class. I'll come back to that question a little bit. Yep. Before we do that, what did I want to say here? Oh, I want to make a couple points. So what if I bringing this down step by step, hopefully it's easier to see this. What's the lowest my variance could ever be?
0.
0, right? What would a data set with a variance of 0 have to look like?
All the same.
Yeah, all this is not interesting, right? We don't see data sets like that. They have to be they have to have all the exact same salaries, right? All observations have the exact same value. Now, that's kind of helpful though, because prevents me from making mistakes if I forget to square these deviations. Anytime I square something, it becomes positive, right? It doesn't matter if it's below the mean or above the mean, right? So my variance should always be positive. Okay. And we'll kind of use this throughout the semester, this idea, but that's a kind of an important kind of concept. I'm going to skip over these slides. This is kind of stuff that we had extra time for. So I don't know, we might revisit it at the end of class or on Friday. I'll see. So if I had this, hopefully, if you're kind of following along, this first question I asked should be pretty easy. So the very first question I want you to answer, and this is, I use these eye clickers and not only to kind of get participation, and honestly today, and my turn today, it's just a couple points of extra credit just because, I know there's a lot of people probably not here because of the weather. But I also use it to kind of get an idea about where we're at understanding concepts. So hopefully if you're following along, the very first question I want you to answer, and I will eventually want you to answer the question that's on the slide, but the first one I want you to answer is, which of these cannot be the population variance for this data set? All right, so I want you to respond to that question first, and then we'll kind of move to the second question. So the first question I want you to answer is, which of these answers cannot be the population variance? And I kind of have a reminder here that that mean is calculated to be 45. And we did that last class. So give you guys 20, 30 seconds or so. Shouldn't be too bad. Which of these cannot be the population variance? All right. Get a response in here. Count to 16. We only got 9 So make sure you're answering which of these cannot be the population variance. 12 of us. All right. I'm going to close it out here. Everybody good?
Sorry, my reach around.
Yeah.
Sorry, so I have to buy-
Oh,
1 second.
you're good. Just talk to me or yell it. All right. I think I got all 16 of us now. So the next one I do want you to work on for a couple minutes. And these are kind of, I want you to talk to the people around you if you're having kind of issues with it. I need to make, I don't need to. I want to make sure you're able to do this by hand. So I'll give you a couple minutes to actually calculate the population variance for this data set, right? This is getting used to using our calculator to answer these questions. So help you out in homework, but also on the exam. So I've got these commute times, I've got the mean. How would I find my population variance? Go through every observation, find their deviation from the mean, square it, write that number down, do that for every observation. Add them all up, you can see the population variance, so we then would divide by the total number of observations that we have. So I'm gonna give you guys a couple minutes, like I said, talk to the people around you as you get working this a little bit. They might know something that you don't know, or might, you might get stuck at a different point maybe. So I'll give you a couple minutes working this, and we'll kind of come together and talk about it. And I guess you already know, hopefully nobody answers A here, right? On to the second question. 15, 20 seconds here to talk about it. All right, if you haven't got an answer in, and take your best guess where you were at kind of during your work. Make sure we get all 16 of us here. All right, close it out. So hopefully we could break this down, make it a little bit easier. So if I were doing this by hand, right, what I would do is write a column out where I look at every observation's deviation from the mean, square it, write that number down, right? So for the very first one, right, 20 minus that mean of 45, negative 25 squared is 625. Then go to the next observation. Not some of this maybe I could even done in my head, right? 35 minus 45. That's negative 10. Squared is just 100. 90 minus 45. That's 45. Squared. That one I probably couldn't do in my head. Maybe it's easy. 2025. This is an observation that provides evidence that there's no variation in the data, right? It's exactly equal to the mean. So the mean minus the mean is just 0 squared. You're just getting a 0 in there. Then you can do this for the next couple observations. Add these all up, you should get 2,900, right? You then have one final step, which is, well, that was like the sum of all the variation across every observation. The variance is our average measure of variation, so we need to divide it by the total number of observations that we had. Okay. Any questions over anything there? Any kind of any of the steps or along that process?
So the mean was 45, that's where you got that to 5.
Yeah, so remember, yeah, so I've got that mean of 45, right? So what I need to do for every observation is find the deviation from that mean of 45 and square it. That's all I did in that column, right? Just kind of break this down step by step. You could have written this all out in one line in your calculator if you really wanted to get like a calculator table to kind of use parentheses and add that many. But breaking it down step by step sometimes helps, prevents from making like little errors or something. Any other questions here? And I haven't forgot about your question about Excel. We'll get there in just a second. So what if I wanted instead, I said, okay, look, and I won't ask you guys this one, I'm not quicker, but let's say we've got calculated my population variance was 414. What if I instead said, okay, look, I know you thought that was population data, it was actually sample data, right? It was only 7 of like 700 employees. So you should have been calculating this as like a sample variance. What's the only thing that should change?
Observation.
Yeah, I don't divide by 7. I would divide by
-1.
7 minus 1 or 6. Dividing by a smaller number should make that value of 414 higher, right? Sure enough, if I divide by 6 instead of 7, right? The first part of the process, nothing changed, right? It's the exact same procedure to calculate a population of sample variance up to the very last step, which is I instead divide by n minus 1 instead of n. Okay? So that shouldn't be too bad. Any questions on that concept? Now, in practice, you're never going to be calculating population sample variances for the same data set. I'm just kind of using that to make a point, right? It's either going to be population or sample data. So I'll leave this up here. Well, let's hop to Excel and then we'll kind of hop back. So we've got this Excel. I kind of went over these last class. I updated this slide. I'll have to re-upload the skeleton slides, kind of have a slight error in them. It's an old function. It was, I think originally it was just std.p. They changed it for obvious reasons. But those old functions I think still will work. When we talked about the variance equation last class, there's also a built-in standard deviation equation, which really all it should do is take the square root of our variance. So it's kind of doing the exact same thing, just adding on that final step of taking the standard deviation for us. So if I open what we were working on last class, so we had the sample variance already calculated down here. If I wanted my sample standard deviation, so we used var.s, it's just going to be stdev.s. I then go over, select whatever variable I'm trying to find the sample standard deviation of, and I'm done. Now, what I could also do is instead of using that built-in standard deviation function, if I've already found the variance, I can use this SQRT function, which basically just takes the square root of something for me, right? So I know that the sample standard deviation should just be the square root of the sample variance. So if I use that SQRT function, find the square root of the sample variance, hopefully, if the built-in function is programmed correctly, I get the exact same value. Right now, it might look a little bit different, but I just got the formatting. So another thing we can do, if we go up here to these little icons, I think I've showed you this before. I can actually change these to show me different numbers of decimals. Now, if I've got the same decimal kind of format, I can see these are exactly the same value. So two different ways of doing the same thing, using that built-in standard deviation function or the square root function. Right? But the other ones we talked about last class, right? So they're already kind of built in there. We'll do some more work in this later, so I'll save it later. The next thing I want to talk about before we get to weighted means is, and I'll try to draw this out on the board first. So let's say, I need to give myself more room. Let's say I have a distribution that looks something like this. And I think if I remember, I'll try to do this from memory. I'm pretty sure what I'm saying here is true. So let's say we've got male and female IQ data. What ends up being true is those means. Sorry, this is an equal sign. The mean male IQ and the mean female IQ are like pretty much the same. I think they're off by like less than a point. Like it's basically the same average. However, if we're looking at the male distribution, the variance is much higher, right? So if instead I was looking at the female distribution of IQ, it's going to look more like this. So it's still going to be centered around that mean, but it's a much lower variance. I'm just making these numbers up. It's not 110, but I don't think the difference is as great as I'm drawing. I'm just using this example to kind of make a point. So let's say I have a much smaller variance. What a smaller variance is telling me is that there's less variation in the data, or that the average variation from the mean is smaller, which means I should have more observations or higher frequencies for the values around the mean, and seeing values that are further from the mean should be less likely, right? Because I don't have as much variation in my data. Values far from the mean are becoming less likely. Values close to the mean are becoming more likely. So when I have a higher variance, or the standard deviation is just scaling the variance, so a higher standard deviation, it should kind of pull my distribution up. Now I do this as continuous. You can imagine the way that we've done, like you could have a bunch of bars here and I'm just mapping out the top of all of them, but it's going to pull that distribution up or give you higher bars in the middle around the mean, lower bars at those values far from the mean. Right. So this on the slide is just instead of having two, going from standard deviations, right, going to smaller ones. The smaller the variance of the smaller standard deviation, the more peaked my distribution is. Right. The higher the variance gets, I'm moving in the opposite direction. Right, it would kind of flatten out my distributions. Right, because a higher variance should mean that the values near the middle are less likely. The values further from the middle are more likely. Right? So this variance or standard deviation visually is going to kind of change how peaked my distribution looks. A lower variance or a lower standard deviation, I'm getting a much more peaked distribution where all my observations are centered around that mean. Okay. Any questions here? I didn't draw this out, but if I have differences in means, all that's going to do. So like, let's say I had male and female height. Something like this. That would just kind of shift my distributions along the x-axis, right? So the mean visually shifts my distributions. If we have differences in means, it shifts those distributions along my x-axis. The variance or the standard deviation will kind of change its y-axis, right? How peaked it is or how flat it is. Okay. Any questions on that before we kind of switch gears here a little bit? All right. So up to this point, we've been calculating means. going to deal with a slightly more complex issue, right? Which is that sometimes my data does not represent like one person or one country, or I guess it could represent one country in this example. But sometimes I have group data. So let's say I wanted to find like the average fast food sales, and I've got, you know, McDonald's, and then I've got like some local, I said Jim's Burger Shaker, right? So some local company. Well, I don't want to simply add up my observations and divide by the number of observations I have, because the observation value that I can see for Jim's Burger Shack represents one company, one location, while McDonald's might represent thousands, right? It's going to be the average sales across thousands of these stores. So I don't want to treat them the same. I want to weight one of those groups higher because it represents a higher number of establishments. Another idea here would be, let's say I wanted to find the average income in the US, but I've only got incomes at the state level. Well, I don't want to simply add off, you know, the average income in every state, add up all 50 states and then divide by the number of states 50, because I'd be treating California like it was representing the same number of people as Delaware. So what I would probably want to do there, if I've got group data and thinking about that income example, using what I would want to do is use as my weights the population of each state. So I've got the equation up there. We'll talk a little more about that in a second. But the idea would be, okay, take, let's say, California's population, multiply that by California's income, then take, let's say, Delaware's population, multiply that by Delaware's income. I would then do that for every single state. And then the final step, well, what was I using as my weight? Sorry. Those are the populations. So I would add up all of my weights, right? So mathematically, how we write this out is, now that I have group data, I'm still going to have this variable X I'm interested in, my income variable, but I'm going to have to multiply every observation value for that variable by whatever that group's weight is. Once I do that for every observation, add them all up. Once I do that, finally divide by the sum of those weights, right? So I have that written out kind of here, right? Just kind of seen it in a slightly different way. Okay? So these are our steps kind of written out. Why that? I'll relate this to what we were doing with the old mean. So with our old mean calculation, when we didn't have grouped data, we said all we have to do is add up the observations and divide by n, because everything was like representing just one person, right? Or one out of however many observations we have. So another way of writing this, we said, what we're really doing is just adding up every observation, dividing by total number of observations that we had. Okay. Now here's where what I showed or talked about earlier kind of helps us see what we're doing a little bit differently, and I think maybe make the weighted mean and the mean make a little more sense. If I'm dividing everything by n, that's the same as multiplying every single thing by 1 over n, right? So now, if I write it out like this, I'm multiplying these here. What I'm doing is, for every observation, I'm taking that observation's value for x and weighting it by 1 out of however many observations I have. What I'm doing with my weighted mean, I could kind of write this out a little bit differently. Notice here, my weight is now not 1 over n, but it's whatever the weight of that group is divided by the total across all groups, right? Or adding up all the weights. So in my population example, this would be like I'm weighting it by the population in California divided by the population in the US, right? Because that group data, the California income, represents this many Californians out of this many of them Americans, right? So we're just changing it from where we're weighting everything equally to where we're now weighting things, to represent that some groups represent a higher number of individuals than others, okay? Does that make sense? Any questions on that? I'll give you another example. I don't know why I'm using this red marker. I'll give you another example of this that I think. So let's say I've got like a class. Excuse me. So let's say 75, 80. So I've got three different things that count towards my grade in a class: this project, exam scores, and my homeworks. Okay? They're each weighted differently, right? Where exams are going to be weighted more than this project. So when I'm looking at these grades, right, I don't want to simply add them up and divide by 3, because I know that this 50 shouldn't be carrying as much weight, or it shouldn't count towards my grade as much as that exam scores, my exam scores at 80. So how would I find my weighted mean here? Well, I'm going to go through every single group, add up, right? For every single observation, take that weight, multiply it by the value for X, do that for every single category, every group here, add them all up. That would give me my numerator, and then would have to divide by the sum of my weights to then get my kind of denominator there, which if this class is set up correctly, the sum of my weights should just be 100, right? Or 100% of the grade. So I'll go through and do that. I could do 30 times 75 plus 50 times 80 plus 20 times 50. And then divided by the sum of my weights. And that's how I would find kind of my grade in this class, or my weighted average, or my weighted grade. Right? Now, breaking this down a little bit differently, you can kind of see here, what's my denominator? It's going to be 100, right? So another way of thinking about this, like for me, this makes sense. Like I calculate this way and like it jives with my brain, but I understand why a different way might help, right? So if it's easier for you to think about, well, this first category is just 30 out of the 100 possible weight, or 100 possible percentage points. So that very first value of 75, I'll weight by 30 over 100. And then the second category is 50 out of 100. So I'll weight that grade of 80 by 50 over 100. And then the third one is 20 out of the 100 possible points. Oh, sorry, I didn't get a 20 on that. I got a 50 on that. Right? So just another way of thinking about it and setting it up. Like I said, some people this makes a little more sense. For other people, their brain kind of works just a little bit differently. Okay. Any questions on this before we keep moving? Okay. So I'll go through a couple more examples here. So let's say you can actually get income data from the US Census, but it's you can't like see every single person. They only give it to you grouped, right? So I went out at one point, and I don't know what year this is from. So it might seem a little odd, but it's got income broken down by gender and rate, like these 4 racial categories. The Census Bureau kind of records things that obviously we can like make this a lot more delineated. But we just got these 4, so we'll just kind of act like those are our only 4 groups. So if we want to have, I've got the mean income for each of these, for males, for each of these 4 different racial categories. How could I find the overall kind of average or mean male income in the US? Well, I don't want to simply divide those up, add those up and divide by 4, because that would be treating like every group represents the same number of people. And I can see, right, there's quite a disproportionate, number of people in some of these racial categories as opposed to others, right? My demographic breakdown is not like an even distribution, right? So I know that this value I've got of 59,000 is going to represent way more people from that original data I can't see, right? The data before it was grouped, then this value of 60,000 really only represents like a 6,000 people. So I'm going to use these number of individuals in each group as my weights. So how would I find my weighted mean? I'll go to my first group, take its weight, multiply it by its value for X. Add that to the next group's weight times its value for X. Then add to that the next group's weight times its value for X. Do that for each of the 4 groups. Once I add those all up, that gives me my numerator. The final step is I need to divide by the sum of my weights, right? This is how we're finding our weighted mean, which I've kind of nice here. I've already given you the sum of those weights, right? At 108,000. Okay. So we break this down, write this out, it looks something like this, right? Where I'm taking every group's weight, multiplied by its value for X, adding them all up, and then finally dividing by the sum of my weights. Any questions? Yeah. Also, you can I moved this box in my last section, so I had like white boxes over here, so it would then kind of not show you the answer, but you could go back, move those on the PowerPoint slide, and actually try to reproduce what those means are. Because you could do the exact same thing for females, it's just that you're gonna have different income amounts and different weights here. Okay. Also, this data is, very sad to see. I don't know, they see the disproportionate income values across race and gender here, which kind of highlights an issue, but that's for a different class, right? We're just identifying what those weighted means are, okay? Any questions on this idea, this concept? Okay. Also, did I answer your question about Excel earlier? Just kind of showing you that we've got these built-in functions for the variance and standard deviation. So I'll show you how we do this weighted mean stuff. Like we want to be able to do it by hand, but I'll also show you that, there is a way in Excel to kind of make it a little bit easier, I think. So I'll show you that here in just a second. Make more of a point here. So let's say instead of race, I've got this broken down by region of the country, right? So if I'm thinking about when I'm calculating this weighted mean, which of these regions income is going to influence the weighted mean that I calculated the most? Should just be, it should just be the one that has the highest weight, right? So if I'm looking at this, the South by far and away has the most, represents the most number of people here. So that higher weight is going to influence that weighted mean the most, right? Just like here, right? 30 out of 100 isn't going to influence that mean. That 75 won't influence the mean near as much as that 80 because it's 50 of the 100 possible kind of points. Any questions on that? Shouldn't be too crazy. Oops. So a couple points here that I'll have to make with this slide. So we can do a weighted mean. We can also do a weighted variance, right? Because now if I want to calculate the variance, I've still got group data. I can't treat it like I was before, right? So all I'm going to do, it's going to be exactly what we were doing before. We're going to take each observation, which is now a group, their deviation from the mean, square it. But now we have one added step, which is we then have to multiply it by the weight for that group. Once we do that for every group, we'll add them all up. And then here I've got it written out two different ways. The denominator really in practice, we're going to be dividing by adding up all of our weights, right? Just like the variance is the average deviation squared, the weighted variance is like the average deviation squared, right? So just like we had for the mean, our denominator is the sum of the weights. But one way we can kind of write this out a little bit differently, and this kind of helps as we're moving forward with some other group data stuff. The sum of my weights should be whatever the sample size was from the data I can't observe before it was grouped, right? So for instance, there's 110,000 males that exist in this data set the census has. They then condensed it down and only gave me the data in these four groups, right? Well, I know that if I've got these four groups and I add up their weights, that should add up to whatever the original data was before it was grouped. So you can kind of think about it as the sum of our weights really represents the total number of observations in that data that was before it was grouped. Okay. And we'll kind of use this some other points throughout the semester, this idea that if we have group data, the sum of those weights should represent the total number of observations. Another good example of this, if we had a histogram, so let's say we go back and I've got my frequencies. Well, just like we said, when I add up those frequencies, they should add up to the total number of observations. Right? A histogram in Excel, when I had the data, was really just taking the data and grouping it into bins. So it's the same idea, right? Adding up the weights just gives us the total number of observations of the data before it was grouped. Okay. So what is this going to look like, right? Well, I could break this down step by step. So if we go back and remember, the mean was about 53,000. And it wasn't exactly 53, but for the sake of just making it easier to talk about, I'll say it's 53,000, right? So what I would do is go through, take the first observation, 59,000, subtract that mean of 53,000, square that value, then multiply it by 73,000. Write that number down. Then go to the next group. Take its income, 38,000, minus the mean of 53,000. Square that deviation to the mean, then multiply by that group's weight of 11,800. Do that for each of these four groups. Add all these values up, and then the final step would be dividing by the sum of all my weights, right? So I think it's at about 110,000 or something we had up there before. So that's what I would do, kind of break it down step by step. You could type that all out into your calculator in one line. Let's see, do I have it? So I don't have it written out, but you can imagine I could just start writing all this out where I've got the first group's weight, which was like 73,897 times that first group's deviation from that mean squared, add to that my second group's weight times that group's deviation from the mean squared. Do that for all four groups. Then divide by the sum of my weights. So what? Just writing out the first two will look something like that, right? But I think breaking it down step by step instead of trying to get this all entered into your calculator at one time and making sure that you have this added before you divide it by the sum of the weights, probably a little bit easier to break it down step by step. Okay. Any questions here? Yeah.
So once you like add all of it up, like the numerator,
Mhm.
you add like.
Yeah, so I skipped this step here,
Okay.
right? This was after I divided it by the sum of the weights,
Okay.
right? So,
Add it all together.
yep, so I'll add this up first, maybe then write that. I want to break it down even more. Write that number down. That's my numerator. Then add up my weights. That's my denominator. Now I kind of do that calculation. That would give me 94,000. Okay. I'll break this down in Excel too to kind of show you an easy way to do this in Excel. That would match kind of how you could do it by hand, breaking it down really step by step. So first thing I'll do is copy this. And then I'm going to go to a new sheet in Excel. I have to figure out why. So if you got a PC, when you go to paste, you should have options. On a Mac, someone last class was trying to do it and it was like graying it out for them. I'm not sure why. I think it might be something to do with like they're trying to copy it from PowerPoint because it's a Mac. It wasn't recognizing it, but it should allow you to not match this or keep source formatting, but simply match the destination. So it doesn't give you like all this crazy formatting stuff. Really, we just wanted to get these values, right? And I'm going to delete this. So let's just say I've got my mean income and the number of people in each one of these categories, right? So the very first thing I'm going to do is calculate the weighted mean, but break it down step by step, right? So the first thing I need, I think I've got this erased now, but remember for our weighted mean, it was the sum of our weights times the X values divided by the sum of our weights, right? So the very first thing I'm going to do is go through every observation, take that group's weight, multiply it by that group's value for X. Right? I'm then going to copy this down. They'll update my cell references so that I can do this for each four of my groups pretty quickly. Right? Now, the other thing I'm going to have to do is add up those weights times the X values, right? And that would represent my numerator, right? Now, I also need to find my denominator, which is the sum of all my weights. Right? I now have my numerator and my denominator. My weighted mean should just be the sum of those weights times the X values divided by the sum of my weights. Right? And I didn't click with the mouse. You can kind of use the keys to navigate, notice, and it changes that cell reference to wherever you kind of stop that cell. Hit enter to get out of the cell. Sure enough, I get that 53,000 as my mean weighted mean income. Okay. Questions over anything there? I went through it kind of quick, but it's just really, do a whole lot and really nothing new. We're using Excel dual math for us, right? Now we could also find our weighted variance. So what we're going to need there is we're going to, well, actually, sorry, this isn't the sum of, this is the sum of them. Here we go. Let me make this a little bit more. There we go. So, and then this one's not a sum yet. I'm just showing you that that's what we're calculating. Okay? So with our denominator, or weighted variance, our numerator now looked like this, but our denominator was still the sum of the weights, right? So this was our weighted variance, okay? So what I'm going to go through and do, and it's not just that, I need to also have in my weights times that deviation squared. Now, when I write like this caret 2, that kind of represents squaring it, and that's because it matches up with how we'll square things in Excel. So for this first group, I'll take their weight, multiply that by whatever their value for X was, minus the mean that I calculated. Then I need to square that deviation. That's why I kind of have that caret 2, because that's how we would do it in Excel. Have Excel do it for us, right? So a lot of times when I label things in Excel, I'll type it out the way we would do it in Excel just so it kind of matches up, as opposed to like inserting equations and symbols and making them all fancy, right? So I want to do this for every single group. If I copy this down, that's great. We'll update my kind of weight and my income value for the next group. But I don't want it to change that weighted mean, right? The weighted mean, I'm always subtracting the same value. So I need to make sure that I freeze that cell reference, right? Hit enter, copy this down. If I then want to find the sum of weights times this, right? That was going to represent my numerator. So I'll add up those weights times the deviations squared. Nope, there we go. All right, that should give me my numerator. If I then want the weighted variance, well, I've got my numerator up here. The sum of my weights I had over here, right? I already had that from calculating the weighted mean. And that's how I get that 94 million, right? So I can break this down here. I'll write some of my weights here. I can break this down step by step, right? And kind of this matches up with how you would do it by hand. There's other ways to do weighted means in Excel. I'm not going to expect you to know them or go into those, but this is just how you could do it in Excel, breaking it down step by step. If you're working on a Connect homework or something and you're doing this in your calculator and you're not getting it right, but you're pretty sure you're setting it up correct, you know, you can kind of work through it in Excel and kind of see are you matching up with that, right? But when it comes to the exam, someone asked this question. There won't be any like Excel related stuff on the exam until they give me a lab for class. I won't be incorporating Excel into the exam, so we need to know how we do it by hand, getting familiar with our calculators. But along the way, if you want to use Excel on your Connect to kind of help you out, that's more than okay. The other thing I wanted to show you real quick. So you notice these are like really large numbers. I can go in, right click and format the cells. Maybe I don't want them to show or default to that scientific notation. I'll select number, and then I can actually see how big these values actually are. I don't really care like when it comes to like if we have a homework assignment and it's got scientific notation, that's fine. I just kind of more of a general note about Excel that if you want to change the formatting of cells, that's how you do it. I think that should be everything that I want to say. This should allow you to answer a lot more of those Connect assignment problems. We've got 2 more things that we'll cover on Friday that are on a couple of those questions, which are correlations and covariances, as well as how do we do this weighted mean stuff when we've got like histogram data or bins. And it works very similar. Probably could already figure it out on your own, but I'll give you an example of that and show you how it's just a little bit different. Okay. All right. Hopefully the snow calms down, and I will see you guys on